In our study of the temperature effects on action potential amplitudes, we will be studying with earthworms. We chose earthworms because they have large giant nerve fibers that are very easy to record from. We will be recording from the MGF, which sends sensory information from the anterior of the earthworm, and the LGF, which sends sensory information from the posterior of the worm. It is important to note the temperature effects on the kinetics of ion channels. Because will decrease the temperature using ice of the earthworm, the channels will open slower, and they will also remain open for longer. Consequently, our hypothesis for this experiment is a decrease in temperature will result in decreased spike amplitudes by the same factor for both the MGF and the LGF. The MGF has a larger diameter, so we should expect it to have higher amplitudes even at lower temperatures than the LGF.
The materials for this experiment include nightcrawler worms as seen in the plastic container, a bowl of warm water, 2 paper towels, a styrofoam cut into 2 pieces, a paintbrush, a spiker box with electrodes seen as white and red with a blue cable, a computer with a spike recorder program, and 2 bags of crushed ice. Insert the white plug with the ground and recording electrode 2 into channel 1 in the spiker box. Then insert the red plug with the recording electrode 1 into channel 2. Then insert the blue cord in the spiker box and connect it to the computer. Make sure the computer is fully charged as it cannot be plugged in when recording. Switch on the spiker box using the black circle dial. There should be some noise when you turn it on. Then go to Spiker Recorder Configuration Settings and set up the filter in the following parameters: 75 as the lowest, 800 as the highest. Click the box for 60 Hz, and then make sure recordings from channel 2 is visible by clicking the red color. After hitting enter, you should see that recordings from channel 1 is in green and recordings from channel 2 is in red. Obtain a worm from the plastic container and wash them in warm water. This will make it easier to insert the electrodes as well as warm the worm up before recording. Do not anesthetize the worm as it will impact the recordings. Then, dry the worm using a paper towel and insert the electrodes in the worm ventral side up, the whitest part of the worm, in the following configuration. Recording electrode 1 in channel 2 goes to the posterior end of the worm. Recording electrode 2 in channel 1 is placed about 50 millimeters from electrode 1. The ground electrode is placed closest to the clitellum. This is a configuration to record from the lateral giant fiber. To record, hit the record button in the spike recorder program and then place markers to indicate when the worm was stimulated. In this example, numbers 1, 2, and 3 are used for each trial, for a total of 3 trials. The posterior end of the worm is stimulated by being tapped by the end of a brush 3 times in a row with a 1-second pause in between. This is done about 5 to 9 times for each trial. A 10-second pause is also taken between each trial. To record the medial giant fiber, recording electrode 1 is placed near the anterior end of the worm, close to the clitellum, and recording electrode 2 is placed about 50 millimeters away from recording electrode 1. The ground electrode is placed near the posterior end. Recording from this fiber is done the same way as recording from the lateral giant fiber, but with tapping the anterior end of the worm instead. After obtaining recordings in room temperature, the same worm is placed back into the lateral giant fiber electrode configuration, and a bag of crushed ice is placed so that the worm is laying on it and the two recording electrodes are between the ice bag. Another bag of ice is placed slightly on top, making sure to not crush the worm. Recording from the lateral giant fiber in the cold temperature is done the same way as in the room temperature, with the additional step of waiting about 2 minutes before stimulating the worm when recording. This allows the worm to settle and cool down. Recording the medial giant fiber in the cold temperature is also done the same way, using the medial giant fiber electrode configuration in the same ice bag setup.
This line graph shows the amplitudes for the MGF and LGF fibers at both room and freezing temperatures. At room temperature, the amplitude size on average is higher in the MGF fiber than it is in the LGF fiber. At freezing temperatures, the amplitude size, again, on average, is higher in the MGF fiber than in the LGF fiber. We see that the amplitude sizes, on average, overall, were higher in room temperature conditions than they were in cold temperature conditions. Let's take a closer look at the data. In this table, we can see the summarized results from the experiment as well as the amount of variance present. The average amplitude size for MGF and LGF fibers in room temperature conditions was 8.61 and 7.05 millivolts. The average amplitude size for MGF and LGF fibers in cold conditions was 3.88 and 3.30 millivolts. The total amplitude averages between temperature conditions was 7.83 and 3.59 millivolts. The amount of variance between all conditions is within 5 to 10%. For this experiment, we wanted to find out how the effects of temperature on action potential amplitudes in the nightcrawler earthworm. After conducting the experiment and gathering the data, we ran a two-way ANOVA. This is a type of test that evaluates the influence of two independent categorical variables on one dependent variable. Additionally, this test can determine if there are any interactions between our two main independent categorical variables, in our case, the room and cold temperature conditions. The null hypothesis for this experiment is that there is no difference in amplitude sizes between room and freezing temperatures. Let's take a look at the results from our two-way analysis of variance test.
Our first main finding is that there is no significant difference between the amplitudes of LGF and MGF nerves within the same temperature condition. This supports the all-or-nothing behavior of neurons, and our data supports this principle when a statistical analysis was taken and had an F value of 3.05 that is less than an F critical value of 3.98. The second main finding is that there is a significant difference in the amplitude of action potential from a room temperature condition to a cold temperature condition. This means that the amplitude within an MGF nerve in a room temperature condition is larger than that of a cold temperature condition. This is the same for LGF nerves. We see this from a statistical analysis where the F value was 48 and surpassed the F critical value of 3.98 with 1 degree of freedom. Our third main finding is that the effective temperature on each of the nerves is the same. Due to there being a lack of significant difference between amplitudes within each trial for each condition, the spike amplitudes decrease by the same factor for both MGF and LGF nerves. This is seen by the statistical analysis with 1 degree of freedom, where the calculated F value of 0.632 was less than the F critical value of 3.98. Based on our data, our hypothesis was not fully supported. Just as a recap, our initial hypothesis was that there would be a decrease in spike amplitude by the same factor for both the MGF nerve and the LGF nerves. This would be due to a decrease in temperature. We also predicted that the MGF would have a higher amplitude when compared to LGF at both temperature conditions. Our data did not support our portion of the hypothesis where we predicted that the MGF would have a bigger amplitude than LGF at both temperature conditions. However, our data did support our hypothesis when we predicted that there would be a decrease in amplitude for spikes recorded in a colder temperature condition when compared to a room temperature condition, and that it decreases by the same factor for both LGF and MGF. Some limitations to consider with our experiment is that the amplitude of action potentials in extracellular recordings depend on many factors such as the resistance of the tissue between the neuron. We see this with MGF nerve and LGF nerves, as the MGF nerve has a larger diameter than that of the LGF and thus results in a faster nerve conduction velocity, as we have explored in this class in a prior experiment. Another limitation is due to the noise in recordings, such as movements from the worm when it squirms or movements of electrodes, the amplitude of the action potentials of the same nerve may vary. But we also have to consider that the variation of an action potential amplitude is not a deviation from the all or nothing rule, but it can reveal it's a consequence of the recording method. But the main takeaway point of our experiment and our data is that because ion channels open slower and remain open for longer in colder temperatures, the amplitudes of the MGF and LGF nerve decreases significantly in earthworms at lower temperatures. One way that we aim to circumvent this limitation is to use 3 different worms for our recording.